Hi, this is my demonstration on the Bertrand Paradox visualization for the CS6250 Advanced Computer Graphics and Visualization course. I have developed an interactive 3D simulation of Bertrand's Paradox using C++ within the Afterburner engine. Let me begin the demonstration by showing what I have implemented in the GUI. I have implemented three different kinds of Bertrand's paradox, that is random endpoint, random radius, and the random midpoint. I have added three distinct places of the circle as sphere and inscribed triangle as inscribed regular tetrahedron. Let me begin the simulation by simulating the random endpoint method. Technically, the system generates two independent points uniformly on the sphere surface using spherical coordinates and connects them to form a chord. If I click on the add single chord button, we can see that a chord is being added on the two random endpoints. And I have added generate batch button, which will generate the number of chords defined by this batch size here. And I have added timer to speed up or delay the speed of the card generation. And if I let me select the uh, batch size, and if I click on the generate batch button, you can see that the cards are being generated here. Let me delay it for some time. The using the application tracks where cars are overlap in 3D space. These intersections are rendered as density cloud, as you can see here on the screen. The magenta color here is used to specify the most recent intersection occurred between two cores. And for the surrounding cloud, I use continuous HSV gradient defined by code. Blue represents the lowest visible density starting at 2%, which transitions smoothly through green to red. Green represents the median maximum density, that is the 50% of the number of times an intersection occurs at the same point, and the red represents the maximum density. That's the point where maximum number of intersections between the chords has occurred. And I have added an autofocus camera checkbox here. If I check on the autofocus camera checkbox, the camera moves automatically, and autofocus camera tracking system smoothly interpolates the view matrix to follow the newly drawn intersection voxel, keeping the action center so we can inspect the internal structure. Let me decrease the timer so that the number of points drops faster. I have added other camera controls like the zoom to display the field of view and near clipping plane and far clipping plane. We can see that heatmap density in here. The voxel hits is the number of time an intersection has occurred and maximum density displays how many times the maximum number of times an intersection occurred within the same voxel. I have divided the sphere into multiple voxel grids, and when the line intersects within that voxel, a cube will be generated, and we can see the probability in the probability section. Out of 300 and out of this code, the chords longer than the side of the tetrahedron is displayed on the left, which is divided by total number of chords drawn to calculate the probability. Let me decrease the delay. Let me remove autofocus and see from outside. You can see that within the sphere, the voxel cubes are rendered as the color gradient. This blue color represents the voxels with minimum density, and the color changing to cyan, green, and red represents the density with higher densities. You can see that the average probability for random endpoint method is around one third, and the maximum density looks like around the center of the, not actually center, around the circumference of the sphere. Like it's in here. Now let me switch to the random radius simulation. First, I need to select the random radius from the drop down here and specify the number of cards and generate that. For the random radius, the system selects a random random radial direction and constructs a card perpendicular to it. To visualize this specific construction, a yellow reference line, like, let me clear it. A yellow reference line will be drawn and showing the specific radius vector used for the calculation. We can see that with the random radius, the density looks like the higher density occurs near the center of the sphere and density are very less around the circumference. And the probability that the cards drawn with random radius method is longer than the side of the inscribed regular tetrahedron is around the 59 percentage, and it has higher density around the center of the sphere. The white lines here represents the card that are already drawn. You can see that the density is higher towards the center of the sphere, and with flipping plane, you can see it more clearly. And the final method is the random midpoint method. The system generates a point uniformly within the chord length from the midpoint, and if it lies outside of the tetrahedron, the chord will be longer, and if it is inside, it will be shorter. And you can see the yellow reference line for the midpoint. Let me generate in the batch. Autofocus the camera. Maximum density here is 3, and the red represents the higher density area. So the greens are the one within the median. With the random midpoint method, the density are higher near the circumference than towards the middle. With the random midpoint method, the probability the chords are longer than its side of their standard tetrahedron is around 21%. As the number of chords increases, the average probability with the random midpoint method is around 19% from my experiment. You see that? We can see that the density is maximum near the circumference, and it looks minimum near the center. That's all for my assignment on Bertrand's paradox in 3D. Thanks for watching.